So first of all, I'd like to say, apologise for Jonathan Adams not being able to make it tonight. He's unfortunately he was taken into hospital. Anyway, we're hoping he's going to recover and come back and talk to us about the Black Sea sometime in the future. So I'd really like to thank John for stepping into the breach and at relatively short notice putting together a talk on his life history, basically, and the science associated with that. John did complete a degree in maths and physics at King's College in London, and then he went on to University of North Wales in Bangor to do a PhD in physical oceanography. Then he joined the National Institute of Oceanography in Wormley, near to Godalming in Surrey, where I joined him later, about a few years later. And John there worked on ocean circulation of the North Atlantic in particular. That's how the currents in the ocean all move around and eventually control climate. In 1994, he became project director of a big international project called the World Ocean Circulation Experiment, WOCE. Multi-country, multi-institution, a big program. He also took on the role of managing the Climate Variability and Predictability Project, or CLIVAR. From 2002 to 2006, he moved to Scripps Institute of Oceanography in La Jolla in California and became the first director of the Argo project. And John, no doubt, will tell us lots about Argo, basically putting floats in the ocean and letting them travel around and receiving the measurements back from them. In 2006, he continued to work on Argo, but came back to Europe and became the European Public Outreach Program leader. He still continues to do some research and looking currently at the difference in measurements between the 1870 HMS Challenger expedition, physical oceanography measurements, and current day ones. So a very long time series, which is turning up lots of interesting stuff. So John is now going to talk us through a load of that in much more detail. Thank you, John.
Thank you, Phil. Right. You had the short version of the talk. So if you think that's enough, you can leave now. My title is Ocean Observing, 70 Years of Evolution and Revolution, and it is a personal story. In this talk, I'm going to tell you how, from a very simple device developed in the UK in the mid-1950s, it eventually led to the system that tells us what's going on in the global ocean now and is essential for understanding Earth's climate. My plan is to give you some insight into how science is done by people with bright ideas carrying out experiments. The first thing I have to say is that observing the ocean is really hard. The oceans are remote and often stormy. The water is corrosive, deep, and virtually impervious to radio waves and light. Just think, standing on a beach at sunset, look out over the sea. You haven't got a clue what is under the surface. And yet, you can look up to the sky and look at the features on the surface of the moon nearly 400,000 kilometers away. A marine geologist would be curious about the shape and the makeup of the seabed. A marine biologist would want to know about what's living there, ranging from plankton to whales. Ask me, a physicist, and my interest would be in the water itself, its temperature, its saltiness or salinity, and how it moves. So how would you find out about the temperature and salinity of water, not just close by to the beach, but say in the middle of the Pacific and 2 kilometers down? Well, the obvious answer is you'd get on a ship and you'd sail for many days and you'd go out to a remote bit of ocean and you'd lower some kind of instrument into the water to make the measurements, and you'd come back and that would be it. It would be very long, very tedious, and very expensive. Well, that is actually how it was done up to quite late in the 20th century. Small wonder, therefore, that there were so few observations. Up to 1950, there were only 4,000 going as deep as 2 kilometers anywhere in the ocean. But most of them were actually in the North Atlantic, as you can see on this picture here. Here they all are. Large areas had no observations at all. Now here's a similar picture, but these are the same measurements to 2 kilometers depth made in a single month in 2025. There were 10,000 observations in a single month. And it's even better than that, because I or you could sit at your laptop and look at those measurements. They could look at the state of the ocean as it is now. I'm going to tell you how that revolution came about over a period of 70 years. I'll tell you about some key steps along the way. Some were technological, some involved seagoing experiments, and almost all depended on international collaboration between talented scientists and engineers. Since the 1960s, it's been my good fortune to be part of that story. Phil has already introduced you to some of the places, but I'm going to let Google Street View talk about some of them. Here is Wormley in Surrey, a leafy lane. It's on the main railway line from Waterloo to Portsmouth, just south of Guildford, and from 1954 to 94, that was the home of UK oceanography until it moved to Southampton. The second is the quaintly named Woods Hole in Massachusetts. Think of white picket fences, lobsters, and the movie Jaws. From Woods Hole you can take the ferry to Martha's Vineyard or Nantucket. Since 1930, it's been the home to the Woods Hole Oceanographic Institution, known as WHOI. To the north of there, not many miles away, is Boston with MIT and Harvard. All feature in this story. And on the California coast, just north of San Diego, is La Jolla, home of the Scripps Institution of Oceanography. Its roots go back to the early 20th century, and it's named after the Scripps family who made all their money out of newspaper publishing. I've been fortunate enough to have offices at various times within 100 meters of where all those photographs were taken. I now want to introduce you to a Yorkshireman who, in 1954, aged 27, was recruited to that newly established National Institute of Oceanography in those leafy Surrey lanes. NIO, as I will call it, was housed in this rather austere-looking building. Built during World War II, it was where naval radar was developed, and it came with a good scientific pedigree even before oceanography moved in. The cosmologist Fred Hoyle worked there, along with other very eminent scientists who all went on to have fellowships of the Royal Society. So John Swallow's task was to devise a method to measure how seawater moves around deep below the surface of the ocean. You might well ask, why? Well, here's a weather map showing the highs and low pressure areas. Where the isobars are closest together is where the winds are strongest. In the same way, in the early 20th century, Scandinavian scientists worked out that in the ocean you could use measurements of temperature and salinity to calculate the density and hence the pressure. And you can then work out how the water moves at the surface relative to what it's doing deep down under the influence of the Earth's rotation. The problem was that there was no way of knowing how the deep currents moved. You could assume that they were very slow since they were a long way away from the wind, which was perhaps one of the major drivers, but you didn't know absolutely how they were moving. So that was the problem that John Swallow was hired to solve. It turns out that he had a perfect set of skills. He had a Cambridge physics degree. He knew about electronics from some years during World War II when he crawled around over warships mending their radios. He then went on to do a PhD from Cambridge, and he did that by spending 2 years going round the world on another HMS Challenger, a Navy survey ship. There he had found that he really enjoyed working at sea, became an expert on navigation, and his PhD topic actually was developing seismic surveying, the kind that became the mainstay of undersea oil exploration. Through that, he learned something about the compressibility of rocks and of seawater. Using that skill set, he hit on the idea of making an instrument that was less compressible than seawater. He could then just add enough weight to make it sink, and as it sank, it would and the pressure increased 1 atmosphere for every 10 meters. The instrument would become more buoyant relative to the seawater around it, until at some depth its density would equal the density of the water, and it would continue to drift to that level. If he could track it by making it make some sounds, he could measure the current speed and direction. Now, this was an era of post-war austerity, and the new institute really didn't have much money. They'd hired the right person, but they didn't give him much money to build anything with. So let's hear how John Swallow solved the problem.
Yeah, I thought, well, I'll need to use a metal container, and the metal containers that they had already used for this slowly sinking sound source had been made of aluminium, as it happened. And I don't think that was why I chose it. I think I was just looking around for some suitable material that might do. And there was aluminium scaffolding leaning up against the wall outside the institute that the builders had left there. And I thought, well, I wonder what that would be like. And when you do the calculation, you find that it is indeed considerably less compressible than water. But scaffold tubing, as it comes ready-made, doesn't give you much buoyancy.
No, indeed, it didn't give him much buoyancy, so he had to adjust the scaffolding tube. So he put the aluminium in vats of caustic soda, and it fizzed away, producing hydrogen until the wall thickness was correct. He washed the caustic soda off, and so he had a suitable pressure case, and he built these instruments with some simple electronics inside. So the evening might get even better at the end, because my colleague Gwyn Griffiths, who's sitting here, actually a few years ago built a version of that 1950s era electronics. So he will be able to demonstrate afterwards the sounds that Swallow's floats made. Now, almost in parallel with Swallow's inventions, I should say that John, in June 1955, so only less than a year after he joined the Institute, took these prototype floats out to the deep ocean west of Portugal, put them in the water, and indeed they worked. So he'd solved the problem within a year of joining. Now, almost in parallel, another scientist at Woods Hole, called Henry Stommel, had quite independently come up with a similar solution. But it was just an idea. Stommel was a less practical person than Swallow. His idea, also published in 1955, envisaged a huge device, a drum filled with kerosene, setting off explosions at regular intervals. Now, despite being separated by the Atlantic Ocean, and with most international communication being by letter or telex, Swallow and Stommel became lifelong friends and collaborators. Stommel had developed a theory that explained why the strongest surface currents, like the Gulf Stream, are always found on the western side of oceans. Later, with another colleague from Woods Hole, Arnold Ahrens, they predicted that underneath the Gulf Stream there ought to be a southward flowing current. So in 1958, as part of the International Geophysical Year, Stommel provided funding for Swallow to take his devices, now known as Swallow floats, aboard the British Royal Research Ship Discovery 2 to test that prediction. The floats did indeed move to the south. It's one of the few examples of a prediction about the ocean being made and immediately being proved correct. Now, following that success, they decided to do another experiment. Stommel's theory said that far away from the Gulf Stream, the currents would be very slow and steady. This meant that if some of Swallow floats were put there, they would only move a fraction of a kilometre per day. So if you went out with a ship, even once a week or once every 2 weeks, you ought to be able to find them and measure this very slow flow. So they thought they would test it, and again, with US funding, Swallow's floats were deployed south of Bermuda. They would be tracked using a ship based there in Bermuda, and that would go out every couple of weeks. That ship was the Aries. Here she is, a beautiful ketch. That's actually her modern counterpart called White Heather, renamed from the Aries. The same ship is still sailing the seas. You can charter it if you want. So they went out, and the first thing that they found was that the floats this time were not behaving as they should have done. They were hard to find, and when they did find them, they found they'd moved much faster than expected and in seemingly random directions. So here it really gave a clue that the oceans might be much more complicated than these simple theories predicted. Here indeed are the results as they were published in 1960. Measurements of currents at two depths, 2,000 meters and 4,000 meters. Now we're going to go for a little diversion into the subject of underwater sound. Columbia University at Palisades in New York ran a research station in Bermuda studying underwater sound. In 1960, jointly with the Royal Australian Navy, they did what might seem like a rather wacky experiment that was doomed to fail. The Australian Navy exploded a series of 300-pound depth charges off Perth, and the people at Columbia University sat on Bermuda waiting to hear the sound. 19,000 kilometers away. Well, they succeeded. The sound arrived. It took 3 hours 45 minutes to get there. It wasn't such a stupid idea after all. During World War II, it had been realized that at about 1 kilometer depth in the ocean, there's a minimum in the sound speed. It's faster near the surface, faster deep down. And that minimum acts as a channel called the SOPAR channel, and sound gets channeled along it over huge distances. So the people from Columbia University proved this. Whales and dolphins had known it since time immemorial. So, the challenge was now, if the ocean was that variable, this was going to be quite difficult to measure. And we now go back to technology, because Doug Webb, an engineer from Woods Hole, and Tom Rossby, who was an MIT graduate student, designed a version of Swallow's float that would be tracked over much greater distances using low-frequency sound. In this case, about 400 hertz, 400 cycles per second. And here is the prototype that they built, clearly much bigger than the bits of scaffolding tube that Swallow used. It had a range of about 1,000 kilometers and was tracked by listening stations in Bermuda and all around the Caribbean. So this prototype was in 1970 and led to the design of an experiment called the Mid-Ocean Dynamics Experiment, MODE, a joint venture between NIO in the UK and several labs in the USA. It was centered 350 nautical miles south-southwest of Bermuda. So there's Bermuda and there's the MODE area. The area was to be filled with recording instruments, and there were to be measurements made from ships. The sound receivers are these red dots around here, and the new version of the prototype float is this huge thing. Here's a person to scale, so it's 6, 12, well, long, huge, and it worked at rather low frequency, at a frequency of 240 hertz, and if I'm lucky, so that's about what it sounded like. It made signals. They made signals at regular intervals. They were deployed, quite about 20 or so of them. And here's Henry Stommel having a big argument with Alan Robinson from Harvard, who had been on the Aries with John Swallow. And the tracks that these floats made, they were called spaghetti plots for obvious reasons. How do you work out from a plot like that what's actually going on? Well, fortunately, we had some really good computer techniques, a thing called never mind, it's gone. So we managed to work out from this. Here are more plots later on covering the period from 72 right up to about 1990, filling the whole of the North Atlantic. And on the left here, you see tracks showing eddies, which is what they were, moving steadily to the westwards along these lines. So we started to understand the way that that the ocean was variable, just like the atmosphere is variable. But of course, that could only be done where you had listening stations in the ocean. How could you move further afield? How could you move from working just in one area of the ocean to the whole global ocean? Well, in 1978, we have now progressed from observations to a single ship to those observations in the West and North Atlantic. And then in 1978, an oceanographic satellite was launched, the first one dedicated to the oceans. It was called CSAT. It carried radar altimeters that looked down at the ocean surface and measured its shape. Every 10 days, It would go along one of these paths, and so there were repeat observations. Here's a section looking across the Gulf Stream, across from the interior, and then you come to the Gulf Stream and you find that the sea level drops by about 1.5 meters across the Gulf Stream. You didn't know that. So now you could actually map the shape of the surface of the ocean globally for the first time. And it ranges by something like 4 or 5 meters globally. And within these shapes you can see the gyres where the strong western boundary currents are on the western side. Now, CSAT only lasted 100 days. It failed catastrophically. Conspiracy theories said that it was actually turned off by the US military. Why? Because the radar showed that not only could you measure the shape of the ocean surface, but you could measure its roughness, and it showed, here's a ship, and here's its wake. And you could do the same for submerged submarines. Well, maybe we didn't want the scientists getting to know things like that. So it was turned off. So by the early 1980s, these promising results had accumulated from the satellite-borne instruments, and supercomputers were by then capable of running quite realistic models of Earth's atmosphere and ocean. Together, these two factors raised the prospect for the first time of a global experiment as part of the World Climate Research Programme. It would collect the ocean data needed to test how well those models reproduced the climate. Planning for this experiment started in the early 1980s, for observations starting in 1990, to coincide with the launch of European and US altimeter satellites. The experiment was to be called the World Ocean Circulation Experiment. The observational mainstay would be temperature and salinity measurements along that complex grid, with still large areas unsampled, lowering not just simple water bottles and thermometers, but complicated devices costing many thousands of pounds and lowered in the roughest of seas down to the seabed. That ship survey took 7 years to complete. It used all the major research ships in the world, some of which weren't big enough. And so here's one getting lifted out of the water, ready to be cut in half and lengthened. That happened to, I think, 3 ships during WOS. However, there was one essential component missing: the ability to match the mid-depth circulation at global scales. Using acoustic tracking was prohibitive. You couldn't put listening stations all around the world. You needed some other way to do it. This is where 2 other scientists, Russ Davis from Scripps on the right and Doug Webb from Woods Hole on the left, collaborated to produce this device, a float not unlike Swallow's float, but capable of being tracked anywhere in the ocean. And it did it by drift, as Swallow's float was, put in the ocean, sinks down to some level, drifts with the current at that level, and when you want it to come to the surface, you pump some oil from inside the float into an external bladder, like a balloon. The balloon expands, the volume of the float has increased, its mass has stayed the same, it's become less dense, it comes to the surface. It talks to a satellite and says, "Here I am," and when it's confirmed that the satellite has received the data, it sucks the oil back inside and down it goes. That was a very clever device. And so there's the sort of cycle. Once every 10 days, drift for a week or 10 days and come to the surface, taking several hours to come to the surface. So during WOS, several of those, what they were called ALICE floats, Autonomous Lagrangian Circulation Explorers. We know acronyms, but we'll just call them ALICE floats. They were deployed along those lines that I showed you, that the ships went along, and they eventually spread out, and here are the tracks of a whole lot of them filling the South Pacific. Nobody had ever managed to do anything like that before. Now, if you've got this device coming regularly up through the top kilometre of the ocean, why don't you put some device on it that will measure temperature and salinity and relay that to the satellite as well? So later on in WOS, that is exactly what happened, and the ALICE floats became what we call profiling ALICE floats, PALICE floats. So we had both kinds, and by the end of the experiment, some 1,200 of these had been deployed. So let's talk a bit about the oceans and climate. WOS was groundbreaking in terms of being able to observe the oceans globally. It was also expensive. The best estimate we have is that it cost the 21 countries who were involved about $2 billion. About 1.6 million of that was on the satellites, so we oceanographers didn't use too much of the money. It was also timely. The first report of the Intergovernmental Panel on Climate Change, IPCC, was published in 1990, and it called for the establishment of a global ocean observing system and the development of major new systems to obtain data from the oceans. Well, there's an invitation to oceanographers to get involved in climate. Henry Stommel, a little before that, had also a bright idea. You've heard about his kerosene-filled drums. Well, he had an idea, and this is his idea, of a world ocean observing system, a WOOS. He called it the Slocum Project, named after Joshua Slocum, who was the first person to circumnavigate the world single-handed in a 37-foot sloop called the Spray between 1895 and 1898. The heart of WOOS was a worldwide array of robotic instruments reporting their data to weather centres. At the time he wrote it, those systems really didn't exist. Now, both the IPCC, as I mentioned, and the Second World Climate Conference in 1990 called for the establishment of a global ocean observing system, a GOOS, not a WOOS. And in September 1999, a couple of years after WOS observations finished, there was a conference in Saint-Raphael in the south of France. Here it was. It produced a 600-page report. Now, the preparation for that conference got groups of scientists to write a set of white papers, and two of them were proposals for an observing system based on versions of Swallow's floats. And indeed, those eventually came together to coalesce into one proposal called Argo. And its plan was to deploy 3,000 drifting profiling floats that would fill the world's oceans and relay information about temperature and salinity. So from 2000 onwards, Argo became the centerpiece of the global ocean observing system. Argo was very clever when it was set up. It set out a few rules. First of all, there was going to be no central pot of money. Nations had to contribute to funding their own scientists. It also said that data couldn't be hoarded. It had to be shared in real time as much as possible. In fact, 90% of it was exchanged and available within 24 hours of an observation being made. And there was to be free and open data sharing, no withholding of data. Now, this was really quite revolutionary, because scientists like to hang on to their data. They certainly want to hang on to it until the papers have been written. So these were the Argo was started to be planned by a science team consisting of scientists from 7 countries, including the UK, and here they are. So here's Argo as it is pretty much today. This is, well, actually this picture is February 2019, but it pretty much looks like this today. Today there are 4,000 Argo floats bobbing around in the ocean, a map that looks like this. These are color-coded according to the country that deployed them. The green ones are from the USA. That's about half the array. Here there are, I think, 25 countries contributing. Over time, there have been as many as, I think, 37 countries, including some very small ones like Gabon, Lebanon. Because the infrastructure was there, a country could operate a single float, which costs today about $20,000, and then a similar amount for the processing and maintaining of the system. So something like $40,000, a country can be part of this big global international experiment. So, did Argo, the successor of Swallow's scaffolding tube float, succeed? Indeed it did. The first floats deployed in 2000, the 3,000 float target reached by 2007, and now 4,000 floats operated by 27 countries. Argo technology has advanced. Now these floats can measure under ice. They can go not to 1 kilometer, but right the way down to the sea floor. And they can measure the biology of the ocean as well. So Argo has become really the mainstay of observing the ocean. And they contribute about 150,000 profiles a year. So when you work out that you have to deploy about, let's see, about 900 floats per year at $40,000 each, it works out that every profile that you measure costs about $300. Well, that's certainly a lot cheaper than it was to take a ship from the coast of California out to the middle of the Pacific. Up till now, there have been 7,600 science papers published based on Argo results, and even better, 500 PhD theses. And indeed, you can go to your computer, and here it is, April 2020, in the middle of the Pacific. You download this data, and here is the profile of temperature and salinity in this remote spot in the middle of the Pacific Ocean. And here's the website that you can go to look at for yourself. So to recap, all these experiments, first of all, Swallow's float in 1955, then the collaboration between Swallow and Stommel and the Aries, discovering ocean variability. Oh, I should have said that as well as MODE, there was another experiment just a little earlier called Polygon. It was run by the Russians, and I was one of only 5 people in the world who was on both the MODE experiment and the Polygon experiment, but that's a different story. So then we had the CSAT satellite, Woest and Alice floats, Stommel's vision of ocean monitoring, the Ocean Observing Plan for Global Observations, and then Argo starts. Argo the name. Well, it started off as an acronym, but it's actually paired with some altimeter satellites called Jason. So we are all Argonauts. The future, who knows? Will the American floats continue to be deployed, half the array? Who knows? It's a challenge for us. So, Swallow's legacy. John Swallow died in 1994, aged 71. So he never witnessed the birth and growth of Argo based on his work way back in 1955. I hope that he'd have been pleasantly surprised. So, thank you for listening. And by the way, April is a rather significant month. On April the 6th, 1966, John Swallow offered me a job at the National Institute of Oceanography that started this science journey. And on April the 16th, 2019, I gave a talk, somewhat like this one, to a group called Café Scientifique in Launceston in Cornwall. It was my first encounter with Café Scientifique and started another journey. So thank you, all of you, for being my travelling companions.